So this really nice colored, pretty, shiny jewel is a mineral fluorite. Specifically, it's calcium fluorite. And it's commonly used, as a semi-precious stone in jewelry because of how it looks. And many of these stones and this one are formed through precipitation. So you've probably heard this word before. I would hope so. In whatever Chem 1 class that you took, you learned about precipitation reactions and solubility. So precipitation reaction is just whenever you have two aqueous solutions and you react them together and they form a solid. So in this particular case, we have calcium and fluoride ions dissolved in groundwater. They end up combining to form a solid calcium fluoride. And a decrease in temperature causes the overall precipitation to occur if the solubility is exceeded at a lower temperature. So it starts off at a higher temperature, it's fine, it's dissolved in solution, and then that decrease in temperature causes it to come out of solution as a solid. So because fluoride is a weak base, its solubility is also affected by pH. So basically temperature and also pH cause this to precipitate out, but you end up getting this really pretty stone out of it. So we're going to talk more about precipitation and solubility, along with a few more other topics related to equilibrium. So in Chem 1, you learned that in precipitation reactions, you have two soluble compounds that do a double displacement reaction, so they switch partners, and they end up forming an insoluble compound, so a solid. And we learned that these solids don't dissolve in water, they just stay as solids, and that's overall the reaction. But in reality, these insoluble compounds do dissolve to a small extent, so a very small amount of them does dissolve out of being that solid. So we call these sparingly soluble. So by now you're probably thinking that this is what the entire subject of chemistry is like we just, or at least you probably think, oh, the professors just teach me something and then they tell me, oh, that's not true. And it's just the fact that chemistry is a combination of like many different subtopics. So like right now we're learning about equilibrium chemistry, right? So it's very specific. It has to do with aqueous solutions, and we learned a lot more detail. So it's more like in Gen Chem 1, you learn kind of like or you see a more zoomed out bird's eye view of a bunch of different topics, right? And then as you go deeper into different subtopics, so first you're starting off with Gen Chem, and then you go off into organic if you need to, and if you do become a chem major, you take physical chemistry and inorganic chemistry, a bunch of different ones, biochemistry. So as you take each of those, you kind of zoom in further. So a lot of the general things you learned in that bird's eye view in Gen Chem 1, you learn that those general trends do have exceptions. You do learn more details. So that's where we are right now. So don't think like we're trying to confuse you or anything. It's just that there is more to a lot of the general things that we learn at the beginning. So in terms of solubility and precipitation, we are looking at equilibrium, right? So an equilibrium exists between the precipitate and its ions. So you'll have a solid, right? And it's in equilibrium. It's in equilibrium with its ions. So it's very slightly soluble, so very slightly it will dissociate into its ions. So you can see that this K here is very, very small. So it's not going to be a lot of ions in solution, but you can attribute a value to it. So here's just a visual of that same reaction of silver chloride, AgCl. It's a sparingly soluble ionic solid, so when we add it to water, it dissolves very slightly. So here you can see that it's first added to water, and then you can see some of the ions that have come off, right, and dissociated. And it's in equilibrium. right? So it's going back, it's reversible, it can go back and forth. So again, just to recap, all ionic compounds that are termed insoluble actually do have a very low solubility in water, and we can apply the concepts of equilibrium that we have learned to these ionic compounds. So in the same way that we have equilibrium constants for reactions and also acid ionization constants, so Kcs and Kas, we also have Ksps. So these are specific to these solid salts in water, and we call it the Ksp for solubility product. The Sp is that. So let's say we have an ionic solid M subscript NX subscript M. So it's just an ionic compound. So imagine again AgCl just for context, and it's a solid, of course, and then it's in a equilibrium with its ions. So these are just the ions by themselves. So how you would write the solubility product, or the Ksp, is you would take the products over the reactants. Now, remember that when we learned about products over reactants for determining either Kc or Qc, we don't include solids. So that's why in here you do not see the solid. So that's why it's only the ions that we show here. So for example, we have PbCl2, and it is in equilibrium with its ions. So we have Pb2 and then 2 chloride ions. So the Ksp for this, or the equilibrium constant, would be the 2 ions, and we do not include that solid in the equilibrium constant for this. Here we just have some selected solubility product constants, so some Ksps at 25 degrees C. So remember that any equilibrium constant, any K, any Ka, they are all dependent on temperature, because we are using molarities for this, and molarities have volume in it, which is dependent on temperature. Like volume can change depending on temperature. So that's why we specify the temperature that these are at. So we can see that a lot of these are very small. So if you think about that, that means that the products, right, because the numerator, remember the denominator, in this case we don't have a denominator, we just have one. So all the Ksp products, because these numbers are so small, that means that your original values that you had, like written for your concentrations, divided by 1, were very small. And that's why you have such a small number here. So because you had such a low concentration of your ions here, I'm just going to call them ions, overall you get a very small Ksp, which makes sense because these solids, they don't dissolve a lot. They only dissolve to a very small extent to be ions in solutions. So for the most part, most of whatever ionic compound you're looking at is a solid, and only a little bit of its ions are coming off and going into solution. And you can see that a lot of these, yeah, they're very small. Some of them are bigger. This one's very, very tiny, to the negative 36. And these are just a bunch of compounds that we learned about in Chem 1, that we would have looked at the solubility rules and said, okay, when these combine together, these are insoluble. But now we see, okay, they do dissolve to a very small extent. So just to kind of tie that back together to Chem 1. We are going to first practice how to write equations and solubility products. I've presented to you some example equations of insoluble compounds dissolving into their ions, but we're going to go ahead and practice this like from scratch. So if I give you a formula, you should be able to write out the equation for it. So here we are going to write dissolution equations. That's what's happening here. And the Ksp expression for each of these. So we have AgI, CaCO3, and this is something called an apatite. I'm not going to read all of it out, but that's what we're working on. So first we are going to start off with AgI, silver iodide. So we have, obviously this is a solid, right? AgI solid. And it's in equilibrium with its ions, so you're just going to split it up into its ions. So what you have to be able to do is figure out the charges. So a lot of these charges this was part of you learning naming and formulas, being able to write formulas in Chem 1. So iodide is a halogen, which halogens have charges of -1. So I'm just kind of, I'll like bring it up briefly, but that's where I'm getting the charges from. I'm not just like making them up or anything. These charges come from the periodic table. And then silver, it is a transition metal, but typically it forms the charge of +1. And it makes sense because iodide here forms -1, so to cancel each other out, it would be +1. So this is overall the equation for it, the dissolution equation. And next we're going to write the Ksp expression. So Ksp for this would be our ions. Remember, we don't include solids, so we would not include that in here. So it's just going to be Ag plus and then I minus. And then we're going to do the same thing for the other ones. So for number 2, we have calcium carbonate, so it's solid. And then it's in equilibrium with its ions, which is calcium. Calcium is an alkaline earth metal, which forms a +2 charge. And then carbonate is a polyatomic ion, which has a -2 charge, or 2 minus. And then its Ksp would be the ions, not including the solid. And then CO3, 2 minus. And calcium carbonate is typically in like Tums and any OTC chewable antacids. That's like the main ingredient in it. And then finally we have this calcium apatite compound. So we have Ca5. So this one's a little bit longer to deal with. It has more ions. So if you notice, it has calcium. Get the highlighter. It has calcium, it has phosphate, and also hydroxide. So it's not like the other ones that only had 2. So in this one, you would just, take it step by step. Whoops, I forgot to add solid. So for this one, you would take it step by step and just look at each ion. So this is a solid, obviously, and it's in equilibrium. So we have 5 calciums, so that subscript comes to be a coefficient for the calcium. Calcium, again, 2+ charge. It's an alkaline earth metal. So we have that one. And then for phosphate, we have 3 of them. So that is going to turn into a coefficient. So it's going to be 3PO4. And then the charge for phosphate is 3 minus, aqueous. And then finally, we have 1 hydroxide, which is just minus, and then aqueous. So the Ksp for this would be, again, a little bit longer, but it's just the ions. So remember, for equilibrium constants, we do take into account stoichiometry, so we are taking into account those coefficients, okay? So we are going to have calcium 5 raised to the 5, and then we have phosphate raised to 3, and then we just have OH minus. And that's our Ksp for that last one. So again, like I mentioned, our equilibrium constants, in these cases, Ksp, they have a fixed value at given temperatures. So if you remember that little table we looked at with all those Ksp values, they were all at 25 degrees C. Here for this particular example, we have a Ksp value of this at 25 degrees C. And overall, the product of these 2 ion concentrations at equilibrium have to equal this value, regardless of which direction the equilibrium is approached. So if you look at reverse versus the other way around, it's going to be the same because we don't have that solid taken into account here. Here we have an equation of a solid dissolving, obviously, and we are going to calculate Ksp from equilibrium concentrations. So we have a concentration of calcium in a saturated solution of CaF2, and it is this. That's the concentration of calcium. What is the solubility product? So I would start by first writing out the solubility expression, the equilibrium expression. So we have Ksp equals to the ions, and remember to take into account the stoichiometry. So calcium 2 plus, and it's just raised to 1 because that's the coefficient. And then for fluoride, it's raised to 2. So we have that down, right? Because overall, that's what we're calculating, the solubility product, the Ksp. So we need to establish that first before we start plugging anything in. Now, they tell us that the concentration of calcium is equal to 2.15 times 10 to the negative 4th molar. Where are we going to get the concentration of fluoride? So luckily, what happened here is that we have a saturated solution of CaF2. So whatever has possibly dissolved is all that will dissolve. And we have a concentration of calcium. Because they are both coming from this, since this gave off 2.15 times 10 to the negative 4 molar of calcium, then it's going to give off the same amount, like in the same ratio to fluoride. So because we know the concentration of calcium, the concentration of fluoride is just going to be the same thing, but times 2. So 2 times 2.15 times 10 to the negative 4th molar. And overall what we get is double, so 4.30 times 10 to the negative 4th molar for fluoride. So we're just using that ratio to determine what the total concentration of the other ion is. So now we can go ahead and plug in. So our Ksp would be equal to calcium 2.15 times 10 to the negative 4th times our fluoride 4.30 times 10 to the negative 4th, and don't forget to square that one. And then overall what you get when you multiply this out is 3.98 times 10 to the negative 11th. So that is our Ksp for this dissolution equation. So what we just calculated actually was something called molar solubility. So that is the total amount of dissolved ions within, in solution. So the way that you can establish this solubility equilibrium is you'll add your solid that we, consider mostly insoluble, sparingly soluble, into your water and stir. Eventually the solution becomes saturated, at its own point. It's not going to be a lot, but it'll be saturated with ions. So in other words, the compound reaches its total solubility. So in this saturated solution, equilibrium exists, and that's why we can calculate the Ksp. So we can calculate these solubilities from the Ksp value. What we did just previously right now was the opposite. We had the solubilities and we were calculating the Ksp. Now we are going to calculate the solubilities from the Ksp. And solubilities, again, they're concentrations, so they're just in moles per liter. So basically anytime you see molar solubility, it's just the concentration of the ions in solution after it has reached complete equilibrium. So whatever concentrations for the ions, those are also considered the molar solubilities. So here we are now going to go from the Ksp to molar solubilities. So anytime you're going from an equilibrium constant, a Ka, back to concentration, so in this case back to molar solubilities, you're going to have to do an ice table. So anytime you have any K and you're trying to go back to a concentration, that means you have ice tables coming your way. So we're going to practice that here. So here we have copper bromide, and its Ksp is 6.3 times 10 to the negative 9th. So we are going to first set up our equation. That should always be your main goal. Whenever you don't see it on the problem, most likely for the exam, I'll just give it to you. But if you don't see it, that means you got to do it. So here we have solid copper bromide, and it's dissolving into its ions. Whoops. It's dissolving into its ions, getting ahead of myself, which are Cu. And then we know the charge because of that Roman numeral right there. So it's Cu plus. So copper is a transition metal which can have more than one charge, but it tells us right there what the charge is. And then bromide is a halogen which has it typically forms a charge of -1. So there we have our overall dissolution equation. Now what we can also do is write our Ksp expression. So it'll be your ions, and here everything's 1 to 1, so you don't have to raise anything. And there you go, you got that done. Now what we have to do is make our ice table. So we are going to set up our equation or our components, right? And then it's good because you don't use solids, so I just kind of wrote it for nothing. But just to, show you the idea of it, we don't have to worry about that. Why? Because it's a solid, and for equilibrium constants, we don't look at solids, so just ignore that. So if we are considering the fact that at the very initial point, so initially when you first throw this solid into water, there are no ions in solution. So for initial concentration, you have no ions just yet. When the change occurs is when you get ions, right? When it reaches equilibrium is when you have ions in solution. So at the very beginning, there's no ions in solution, so we have 0. And the overall change for both of these will be positive because these are increasing while the solid is what's decreasing, but we don't look at the solid, so it doesn't matter. But overall it's positive, and it's happening with a change of x. We don't know that change, and we don't know the equilibrium concentration just yet. So this overall is just going to be x. So these are pretty simple ice tables, nothing too crazy. And now we can set up and we can plug in to our expression. What am I writing? Ksp equals our Cu plus, so just so that we can compare it right above it, we have that, right? We are going to fill in our equilibrium concentrations into those unknowns, those variables that we have. So Ksp equals x times x. So basically what you have is the Ksp equals x squared, right? But the good thing is we do have the Ksp value. So we know that 6.3 times 10 to the -9th equals x squared. And to solve for x, we are just going to square root both sides. So I'm going to square root that side, square root that side. Square root takes away that squared, and then what you end up getting is x. So I just flipped it around just so it's like, it actually looks like a math equation. And then I'm going to use my calculator and take the square root of that number, of that 6.3 times 10 to the -9th. And what you should get is 7.9 times 10 to the -5th molar. So now we can go back in and calculate our concentrations at equilibrium. So because we just have x by itself, then we have the concentrations for both of these. So the concentrations for Cu at equilibrium, 7.9 times 10 to the -5th. And then for bromide, it's the same thing. At equilibrium, it's 7.9 times 10 to the -5th. So these are the molar solubility. So I know they have basically like two names, like concentrations at equilibrium, but it's also, for this chapter, we call them the molar solubilities. So we have calculated the molar solubilities from the Ksp by using the ice table and then solving for X. So whenever humans, I don't know about you, but whenever humans need a X-ray, specifically like in their internal organs, the doctors will make them take a suspension of barium sulfate, like you have to swallow it. And the reason that they take this is because barium sulfate does not dissolve. It's considered, overall, quote unquote, a insoluble compound or sparingly soluble. So the Ksp of barium sulfate is 2.3 times 10 to the negative eighth, which means that, it's not going to dissolve whenever you ingest it. And whenever you take the x-ray of it, it actually helps show a lot of detail. So this is an example of how these sparingly soluble compounds are useful in, technology or medical technology.